Hey folks, I'm Alex. I'm the CTO of Espresso AI. We help companies save money on their Snowflake and Databricks bills, and you will see why these papers are relevant to us and what we're doing. These two papers came out fairly recently, and I found them very, very exciting for the obvious headline numbers of 10 times faster than DuckDB, 460 times faster than Postgres. These are sort of mostly interesting to me to sort of go like, look, there is like real headroom in optimizing queries. Like the systems we have are good, but like you can do so much better. And so how did people do so much better? So they took a totally different approach to how we've ever built databases in the past. They decided to take SQL and use LLMs to compile them directly into C++. So here we have like one of the sort of benchmark TPC-H queries on the left, and here on the right is not a full implementation, but sort of the hot loop of the query on the left. The things that kind of like they claim that they did here that are really relevant is like instead of having fully general machinery for how to do aggregations, they're like, no, we are going to allocate, exactly 6 slots for these aggregations, and then we're going to directly compute like the index. So this is not the safest code, and we'll get into that in a bit. But I think like the performance improvements that people are showing is sort of like exciting enough to like overlook this for a bit. So. Here are some AI-generated images from the papers about using AI to generate code. Their pipelines are fairly similar, I would say, but somewhat different. We'll get to them in a second. They kind of, they have some pipeline where they're like taking the like workload specifications, which is the sets of queries that they want to optimize. So usually a whole sort of like benchmark suite, either TPC-H or one of the other ones that they've decided to optimize. They figure out how they're going to store the data for this benchmark suite as sort of a one-off operation, sort of because this has dependencies between the queries. If you need your storage to be optimized correctly for the all the queries you're going to do, not just one of them. So they do this sort of an upfront step. And then in both cases, they go loop with an LLM. So these are kind of like the two pipelines that they have. The GenDB pipeline is a little bit simpler. They have sort of like this stage of things, and they kind of keep looping the optimizer. The BespokeOLAP one is like a little bit more interesting. They start with sort of like a similar like setup phase, but then they have like these 4 distinct phases of first we're gonna like give you like some DuckDB plans and tell you to like go iterate off this. Then they give the LLM some like trace and timing information, and they give it some expert knowledge and then some references. So it's not fully clear from the papers like how much of like all of this is exactly useful, or at least which parts of it. But like these are sort of like the embers of like a system here, and so. This is kind of like a chart from the BespokeOLAP paper that kind of looks at like, okay, how did query performance go, among other things, when they iterated things. The blue line is the sort of like most relevant part, which is like how much faster is it getting, and I think the most interesting like takeaway from this is really this like purple section where like giving it information about execution is the most impactful thing, as opposed to expert knowledge or anything like that, which kind of makes sense. Like LLMs are very good, when you could actually like give them feedback about exactly how their like optimization process is going. So yeah, and this sort of is like, I was kind of curious, like what is the expert expert information they're giving to this sort of loop in this green section? Surprisingly very limited. It's literally like these bullet points, like this summarized a little bit with an LLM, but very, very simple stuff that they're giving it. So yeah, a little bit of a tangent. These papers, the GenDB and BespokeOLAP ones, look a lot like the ML papers for doing automatic ML research. So this is like a diagram I stole from a different paper, which is like the ML Evolve paper on like, improving, LLM's ability to do, ML tasks of like, Kaggle and things like this. And you can see these pipelines a little bit more sophisticated than what we see in the like GenDB or BespokeOLAP cases. I think mostly because the literature in this space is just a bit more developed. GenDB and BespokeOLAP papers are the only ones talking about database generation, whereas there's a host of papers grinding on the task of, how do we do ML research better? And there's probably some space for like cross-pollination here. Most interesting thing being they had this like tree search, like evolutionary search, where they like cross-pollinate nodes between each other. But I'm not gonna dwell too much on that. So to get back to the BespokeOLAP and GenDB papers, a question that everyone has when they like see these results is like, how much is it gonna cost me to loop on, an LLM for a long time? Surprisingly affordable. So I don't know if this has a pointer. Cool, yeah. So like $30 for GenDB and like $120 for BespokeOLAP, which is like much cheaper than a software engineer if you want to do some optimization. One of the sort of like hidden costs that's not really talked about is sort of like these numbers that I got out of some notebooks they had in their repo, which is like how many times did they have to actually benchmark the queries to get these results? And this is like across the whole benchmark suite. So this is something like they ran this benchmark like 30 times per query to get these numbers, which, if you're doing like small scale experiments, like this costs you absolutely nothing. If you're trying to like actually optimize some pipeline that's costing you like hundreds of thousands of dollars a year, like running the same pipeline 30 times is probably not realistic. So just some food for thought on like where we go from here. Okay. So what actually happens when you like run this optimization? This is sort of like GenDB on the left, BespokeOLAP on the right, of like what do these LLMs actually do? And I think my main takeaway from this is just like they do a whole lot, right? Like they can do like very, very specific optimizations that there's no way you're going to be paying an engineer to do for your specific queries, right? Like they did some like classification here of like, is this a classical or exotic optimization? Which I don't know how much I believe that categorization here, but it is sort of interesting. You go like, hey, this like compact date optimization is only relevant on like 1% of, like 1.5% of queries. So I guess columns here. But like these tiny optimizations, like there's no way you're gonna be spending like a ton of time putting this into your query engine. Whereas, if it costs you absolutely nothing to do it because the LLM is generating it, like all these sort of like niche optimizations become like actually pretty reasonable. So trying to think also through these papers of like, hey, what can we take away from them besides, queries can get faster? I sort of went looking for like various ablations that existed or were possible. So I found these two ablations from the papers. The first one was sort of like ablating their sort of like multi-step agent like loops versus just, hey, what if we just have like a single agent that just like does the whole thing? And you can see that like actually this complexity that they've got with like, the like multiple stages of optimization, like it is buying something, right? Like the lower here is better, right? So this is execution time. So you can see like this like multi-agent setup they have, like this red bar is generally like faster than these single agent things, but so some of the measurements are noisy, right? Like here it's not doing anything, but there's some indication that these loops are like actually useful and not just total fluff. But these papers don't really like break out which parts of these like systems are really like super useful yet. The other interesting ablation that was in this like BespokeOLAP paper was this question of like, okay, how much benefit are we getting from storage optimization versus the actual computation optimization, the actual like micro optimizations, and it's about like half, I'd say, right? You get like a 5 times speed up versus an 11 times speed up on like TPC-H. On this other data set, it's like basically nothing, right? So this is, I think, interesting in 2 ways, right? This shows that, like, okay, we don't have to completely overhaul our storage systems to get, and like our data formats to like benefit from this. Like, you can optimize your stuff that like reads and writes Parquet. You don't have to like re-engineer the entire universe. But it also shows that like, hey, actually there is a benefit from re-engineering the entire universe. So I think like, one open question here is going to be like, how can we like really bridge this gap in a way that's sane, as opposed to, like a simple prototype like what these papers have done. And then this final ablation here, which I think is sort of the bitter lesson for everybody writing an LLM paper ever, is that the most important thing to your results is what model you use. So this is from the GenDB repo. This isn't in that paper, but they had results for all their paper results were like Sonnet 4.6. And if you just like upgrade to Opus 4.6, things get 4 times faster. This is the conclusion of a lot of agentic papers that I read recently, which is just wait for the next model. But hopefully we'll get like clearer, evaluations of like what is and isn't useful beyond just like, new model releases at some point. So, okay, yeah. So what did we learn? I think like one of the things we learned is that like the amount of tokens you use is important. This isn't a thing that the papers say, but it's one of the things that we should keep in mind when we're looking at plots like this that sort of say, oh yeah, we did this phase and then we did this phase and we did this phase and we did this phase. Like, how much of this like phase is important versus just, hey, we just like let the LLM keep grinding? Was like the human reference doing literally anything, or would like, just extending this purple phase have gotten to the same place? I don't know the answer, but I think if you do an evaluation, you should ask yourself that question. And like, this seems sort of like at least convergent with the wider literature of like, hey, we're going to do like some sort of like evolutionary search, and we're going to do some like optimization. The next question to me is, like, are we prod yet? Can we just like ship this? And I think the answer to this is no, unsurprisingly, we are not production ready yet. The main thing which I'll talk about in a second is like correctness of these things is still, not guaranteed. The way that both of these papers evaluate correctness is they run the query on DuckDB and then they run the query through their own engine and they compare the results. And if the results are the same, they say we've succeeded. We'll see in a second that that's not quite enough. The other thing is, yeah, like running 30 benchmarks a query, like that's expensive. I think we need some way of like, being able to extrapolate across query scales so that we're not having to do like, $10,000 worth of benchmarking to optimize our query. And then, the sort of like data storage question, I think like, we've seen that there's benefits from having optimized data formats, but there's no story in these papers anywhere. Like, how do we actually like interop with any other system? So I kind of wonder if this is like an indication that like, any blocks or Vortex or these other systems that, embed like WebAssembly decoders in their file formats are gonna, like maybe see like, a bigger reason to exist. Like you can decode like Vortex and DuckDB with an extension, right? So you could write a data format that like, these LLMs know exactly how to read, and then also, DuckDB can read. Anyway, so correctness. So this is the headline query from the like top of this talk. This works exactly if your values are like what is in the data set. So this like has this line status map for values, and it looks up your line status in this line status map. So if you have any data that's in your data set that is not an F or an O, this whole thing like just doesn't work. It just like starts returning the wrong results. It at least doesn't crash, but it does return the wrong results. And like this is sort of like a big limitation of when you just use execution results for correctness, and why I think that like formal verification is the path forward for this sort of thing. But you can see why we're not like shipping this right to prod. And this is like a query from like BespokeOLAP that one of our collaborators looked at and found. It's like this query has like this like limit 20 that you start with, and it just gets absolutely dropped from the query. And because you are not, because this doesn't return more than 20 results, usually like the queries look the same when you execute them. This one's sort of like a little more niche, that like, you know, the semantics are not quite right. Like, you know, should you be returning like 0 or null? Like, this is a specific thing, but, you know, a little bit more detailed. And sort of like on this note, this is like a problem that everybody faces when they try and do any sort of, you know, correctness evaluation on the generated SQL or data processing. Like, this is from like Snowflake's R2 model, which they were like using reinforcement learning to train. They find sort of like, you know, these top-end queries, distinct queries, joins, they've ended up just like hard coding these patterns into their like text SQL pipelines to sort of go, hey, like, you know, should be really, really careful about all these things when we're generating them. But like, this isn't a scalable approach at all. Like, you know, we'll get somewhere with this, and like, you know, when you have humans reviewing your SQL, this is like all totally fine. But if we want to build actual systems, it's probably not quite enough. So I think that's like all I had from the papers, but I wanted to end this on an anecdote of trying this approach myself. So this was a query that I grabbed from some like analytics we were doing in like our products. We were looking at, you know, the query logs, and we were looking at like the table storage metrics. And we kind of just wanted to know when was the last time someone referenced a table, and how much data, you know, is that table using. So this query conceptually is very straightforward. It's tokenizing every query with a regex. So just finding like anything that could potentially be a table name, and then joining that to the list of table names to sort of go, okay, this is, you know, like false positive prone, but better than false negatives, right? But this is, you know, like just a way to find like when did you last reference a table in the query text. We had this running in like a DuckDB pipeline, and for like small scales this is okay, but at some point this just starts exploding. You know, DuckDB decides to like make a literal row for every single token here, which, you know, if you're generating 100,000 rows per query, this is gonna explode, obviously. And, you know, other systems are better. You know, checking this into Snowflake, it runs in like 22 seconds, it's fine. But, you know, I did try this sort of like GenDB, like BespokeOLAP type approach, but like with myself like in the loop, not fully automated, to just see like sort of like what's possible in this space. And so I like, you know, had Codex like grind on this for like, you know, quite a while, probably a few hours, and like gave it hints when I thought it was doing something wrong. But like, you know, you can just tell it like, hey, I want it to be like multi-threaded. You know, it can figure out things like, hey, I can just like have a C++ version of this like exact regex, not a whole regex engine. You know, a whole bunch of stuff. Like, I think like the most exciting thing to me was when I was like, okay, this seems like a thing that could be maybe improved with like some SIMD instructions, and it couldn't really get it by itself. But if you dump the like SIMD JSON paper into an LLM and say, hey, like read this paper and go optimize this thing, like using SIMD, it's like, oh yeah, I understand that. Yeah, the only downside is I have no idea if it's correct. It's like 3,000 lines of C++, and I don't want to read it. So it is not an app product. It's currently just an experiment. All right, so I think that was all I had to talk about these papers. So if you guys are, you know, interested in working on making databases more efficient, get in touch.